Today we're going to be looking at net change problems, and for the first three examples, we're going to look at equations or algebraically. First problem involves marginal cost. Let's go ahead and take a look at the definition of marginal cost. It says the cost of producing one additional unit of a product or service. Okay, so suppose you make toys. How much is it going to cost your company to make one more toy? Or a unit is usually in thousands. So how much is it going to cost you to produce 1,000 more of those toys as a company? The reality is that number changes as you increase more and more, less and less. So let's read this problem together. The marginal cost of producing X computer chips, so we're talking about computer chips, in units of 1,000. And that's important because, as a company or as a factory, whatever, you're typically going to be looking at in terms of thousands, since you're mass producing. So the marginal cost is C prime of X. So we're talking about a derivative. So the marginal cost is actually a derivative formula, and it tells you the rate of change of cost. So we're going to take a look at the graph to help you understand a little bit more. But here's our equation. C prime of X equals 300x squared minus 4,000x plus 4,000. It says find the cost of increasing production from 10,000 to 15,000 chips. So in reality, they're giving you a derivative formula, but they're asking for the cost of increasing production, which is actually involving the original. So again, we're going to take a look at the graph to get some clarification as far as what marginal cost is. So without further ado, before we solve it, I want to show you what the graph looks like. Okay, so here, this green graph right here is our marginal cost, okay? I'm going to talk about the area under the curve from 10 to 15 in a minute, but here's what I want you to understand. Let's just take a look at 2. So 2 here is going to represent 2,000 chips. So the blue graph is C of X, not C prime. It's actually going to give just a simple cost formula. So for example, if I produce 2,000 computer chips here at 2, it will cost me $72,856, or the computer chip company. If you divide 72,000 divided by 2,000, that is around $36 per chip. Okay, so that gives you an understanding as far as what the original means. So what about marginal cost? Marginal cost is this green graph, which is C prime. If we look at the Y value there, we get 33,200 at 2,000. So what does that mean? Well, this just gives you the slope of the tangent line here. So what marginal cost means, in this case 33,200, is that at a particular point in time, for every increase in 1,000 computer chips, it's costing you $33,200. Again, if you divide that, you get around $33 per chip. So each increase in chip at that particular time is around 33. A good way to a good analogy would be speed, okay? 33 miles per hour. For every increase in hour, you go 33 miles. In this particular case, for every one increase in chip, the cost is going up by $33. Now, I do want you to notice something about this graph, even though this isn't going to be the question, but there is a sweet spot here. If we drag this point down, we can see that the marginal cost actually goes down for a while before it starts going up again. That's important. As a company, you actually want to hit that sweet spot many times, because that means the cost for producing X amount of computer chips, in this case, is going down. So for example, when you're producing 6.67 thousand computer chips, the cost of increasing each chip would be about $26 over here for each additional chip instead of 33 over here. Of course, cost and demand comes into effect, but again, it's just the slope of the tangent line of the cost function is what marginal cost is. So I wanted to get that out of the way before we go ahead and answer this question. So the reality is, again, we're going from the derivative to the original. So if we're looking at the cost of increasing production, really what we want to do is find the original function C, given this formula. And because we're going from one value to the other, we will be taking the definite integral. Remember that for net change, you just simply find the definite integral for your particular x values that you're given. If it's total change, you have to do a little bit more, because total change involves the entire end of the graph ensuring that it's positive in case any part of the graph is below the x-axis. So for step 1, when solving a net change problem, You want to write out the general formula for net change. Now we're going to get a little bit more specific here. If you take the integral from a to b of marginal cost, you get the net change of cost, or the change in cost. In this case, we want to figure out the change in cost from producing 10,000 to 15,000 chips. So this is important because the cost per chip changes. This is a formula. Okay, I know that if you look at this graph, it kind of looks like a line. It's not. It's actually a cubic formula. I'm not sure if you can see that over here. It's not a line. So the change in cost per chip, well, it changes as you increase. Okay, and that could be for different reasons for the factory. The factory just might not be able to produce that many chips, so you might have to build a different factory, which of course is going to jack up the price of cost per chip, and just different, your resources you might have to produce the chips, whatever materials you're using. There's a lot of different reasons why that would be. So if we integrate marginal cost, we will get the net change of cost. Step 2 is going to be to determine the limits of integration. In this case, we're going from A to B because we're going from 10,000 to 15,000, but the formula is already in units of 1,000 already, which is kind of crazy. That means that you have to take your x values and divide by 1,000. So my A value is going to be 10, meaning 10,000. I'll just write that over here. And the 15 is going to represent 15,000. And again, that's because our formula is already in terms of thousands. Step 3 is to determine the rate function. It's already given to you. This is our marginal cost function. C prime of x equals 300x squared minus 4,000x plus 40,000. So, if you're just looking at this and if you can't see the graph, if you plug in 1, you're going to get something around 36,000, 36,300 exact, for each increase in 1,000 units. As you're producing 1,000 units, the cost is going to go up by 36,000 or $36 per chip. Okay, let's go to step 4. By the way, this is actually a simple, lesson. We're doing these steps, but in reality, you're just integrating a function, a rate function, and you're finding its definite integral to get the net change. All right, step 4 is to determine the definite integral. The integral of the rate of change equals net change. So we're just going to find the antiderivative of this and then plug in 15 and 10. So you're going to be using the reverse power rule for integration or antiderivatives, and then plugging in 15 and 10. The antiderivative ends up being 100x cubed minus 2,000x squared plus 40,000x. We're going to plug in 15, and then we're going to figure out what that is. It's basically your upper limit. You get $487,500. What does that number mean? That means when producing 15,000 computer chips, it will cost you this much amount of money. If you took this and divided by 15,000, that would give you the cost per chip. You can see that on this graph that it starts to go up right there, and in fact we can't even see the blue graph because it skyrockets so much. This is one reason why we have calculus, because if we just find the area under this curve, this number right here will give us the change in cost, so we won't have to actually figure out, we won't have to see what the graph looks like at 15 for the original function. But anyway, we do get the y value of 487,000 approximately when we integrate that. So that's over 30,000 per 1,000 chips if you go up. All right. Next, we're going to plug in our lower. So plug in 10 or 10,000, and that costs 300,000. So that's right at $30 per chip. And then the net change is just the upper minus the lower limits that we plugged in. 487,500 minus 300,000, 187,500. Step 5, which I had to write in later, was answer verbally. So in reality, the way we would answer this practically is that it will cost $187,500 to increase production from 10,000 to 15,000. You could take this number and divide by 5,000, and that would give you the cost per chip of going from 10,000 to 15,000. And so that would be around $37.50 per chip when increasing from $10,000 to $15,000 per cost. So that's it for marginal cost. It's just the rate of change of cost. Again, and the best analogy is speed. Okay, you have a position function, and then you have a velocity function. Well, marginal cost is just the velocity function of the change in cost, or the cost in it, actually, of whatever you're producing as a company. If you have any other questions about this example, let me know. Oh, by the way, this is the area under the curve finally, and that's confirms our answer from 10 to 15. Gives us the changing costs in producing, going from 10,000 computer chips to 15,000, 187,500.